Hey, welcome back. In this video, we're going to discuss a connection between two of the recent topics that we have covered in class. So in the last video, we started to discuss functions. We went over the definitions and a bunch of terminology for functions. So when we have a function, typically we write it like f from x to y for some sets x and y. And we covered some terms for functions. So this set right here on the left is our domain. This set on the right is the codomain. We also discussed the image. That was the set of outputs for the function if the inputs come up from our set x. And we discussed preimages. The preimage of some element of y is an element of x whose output is that element of y. And it's possible for an element of y to have multiple preimages. In addition to these terms, we also discussed some properties of functions, including injectivity, surjectivity, and bijectivity. We saw a bunch of examples of different functions, and we determined whether they were injective, whether they were surjective, and if they were both injective and surjective, that means they're bijective. A question you might have wondered is, what's so important about these properties? Why do we even care about them? And like I said, this video is going to connect two recent topics that we have discussed. So one of those topics, as you might guess, is functions. And the other topic is sets. And we're going to talk about in this video how we can use bijections to prove that two sets have the same size. So just to review, we say that the function f from x to y is a bijection between x and y if and only if f is both injective and surjective. And just to review what injective means, and I'll draw a picture for this too. What it means for injective is that any two distinct inputs from x must have different outputs in y. So if we have x over here and we have y over here, and we have two distinct inputs from x, we want to avoid something like this. This right here is bad. So we want to avoid that picture for an injective function. If we have two distinct inputs from x, we want them to have different outputs, not the same output. And for surjectivity of f, we want any element of y. So here's our y, here's our x. So y over here, x over here. If we take any element of y here, we need to be able to find some element of x which maps to y, which maps to that element of y through our function f. So that's just a review from the last video. And if we consider two finite sets, x and y, we can see that if f is injective, that tells us that for every element of x, we have some distinct element of y that we can map x, that element of x to. And that means that the number of elements in y must be at least the number of elements in x. There must be an element of y for each element of x, and there could possibly be more elements of y. So that tells us that the size of y is at least the size of x. And that's true if f is injective. On the other hand, if f is surjective, that tells us that for every element of y, there is some element of x which maps to that element of y. That means that the number of elements in x must be at least the number of elements in y. And it's possible that there's more elements in x than in y. And so this means that if f is surjective, then the cardinality of x is at least the cardinality of y. And so we can see for finite sets, if we have a function that's both injective and surjective, then the cardinality of x is at most the cardinality of y, and the cardinality of x is at least the cardinality of y. And the cardinality of x is a natural number. The cardinality of y is a natural number. If we have two natural numbers, a and b, which satisfy a less than or equal to b and b less than or equal to a, then we have a equals b. So if we do have a bijection f between x and y, we can say that the cardinality of x equals the cardinality of y when x and y are finite. And in fact, this holds more generally. This is also true for infinite sets. So if you want to show any two sets have the same size, all you have to do is demonstrate that there is a bijection between them. And there's a special term I'll mention. We won't talk about a lot of terms today. We'll just talk about a few. And this term is countable. So if you have some set, and it's either a finite set or it's a set that has a bijection with the natural numbers. And remember, the natural numbers are these numbers 0, 1, 2, 3, and so on forever. So a countable set can be finite or infinite, but if it is infinite, it has to be in bijection with the natural numbers. So this is what it means to be countable. We're going to look at some examples of countable sets, and we'll see an example of an uncountable set. So here's a simple example. Let x be the set of positive integers at most n. So I'm talking about 1, 2, 3, all the way up to n. Let y be the set of positive odd integers at most 2n. So we're talking about 1, 3, 5, up to 2n minus 1, because 2n is even, and we're talking about odd integers. And we want to prove that x and y have the same cardinality. And like I said in the last slide, we can prove this by demonstrating that there is a bijection between them. And we can just find a bijection. So we will define a function f from x to y by f of x equals 2x minus 1. Now, we first want to check that the function we defined is actually well defined. This means that for any input from x, the function is going to give us some output that's actually in y. Because it's possible if we mess up the definition that we might find some function that doesn't actually map things from x to things from y. So we need to make sure everything from x gets mapped to something from y. So if x, little x, is an element of big X, that means that it's a positive integer at most n. And then if we plug in little x into the function f, we get 2x minus 1. And if x was a positive integer at most n, that means that 2x minus 1 is odd because x is an integer. And 2x minus 1 is between 1 and 2n minus 1 inclusive. 1 is what you get when you plug in 1 for x in 2x minus 1. And 2n minus 1 is what you get when you plug in n for x in 2x minus 1. So this means our function is well defined because the output 2x minus 1 is an odd integer that is at most 2n, and it's a positive odd integer specifically because it's at least 1. So we found that f is well defined, and we want to show that this f is a bijection, so we need to show that it is both injective and surjective. So for injectivity, we'll use the same method that we used in the last video. We'll assume that f of x1 equals f of x2 for some elements x1 and x2 in the set x. By definition of f, this means that 2x1 minus 1 equals 2x2 minus 1, and we can solve this to show x1 equals x2. That means f is injective. And for surjectivity, we need to choose an arbitrary element of big Y. So we'll consider some positive odd integer that's at most 2n. We'll call it little y. And if it's a positive odd integer at most 2n, we can say that it is of the form 2i minus 1 for some I, which is an element of the set 1, 2 up to n. And if y equals 2i minus 1, then that means that y has the preimage I under f. In other words, what we're saying here is that f of I equals y. Because y equals 2i minus 1, and we know f of I by definition is 2i minus 1. And so we just showed that any arbitrary element of the set big Y, in other words, any positive odd integer at most 2n, has some preimage under the function f. And this preimage, the I, we know I is an element of 1, 2 up to n. And 1, 2 up to n was our set x up here. So f is surjective. And since we showed that f is both injective and surjective, that means that f is bijective. So we showed that these two sets, x and y, have the same cardinality, or in other words, the same size. Now for the second example, we'll consider some infinite sets. Let x be the set of odd positive integers, 1, 3, 5, 7, 9, and so on. So all of them. So it's an infinite set. And let y be the set of the even positive integers. So these are 2, 4, 6, 8, and so on, going forever. And we're going to show that these sets have the same cardinality. We can define this function f from x to y by f of x equals x plus 1. We can check that f is well defined by seeing that for every input from the set x, we get an output from the set y. So if little x is from the set x, then little x is an odd positive integer. And that means that x plus 1 is going to be even. And since x is positive, it means x plus 1 is going to be positive. So x plus 1 is an even positive integer. And that means that x plus 1 is an element of y, which is the set of even positive integers. So that means f is well defined. And we can prove injectivity for this f pretty much the same way that we did in the last slide. We set f of x1 equals f of x2. We use the definition of f to say that x1 plus 1 equals x2 plus 1, since f of x equals x plus 1. And this implies that x1 equals x2. So that means f is injective. And we can prove surjectivity. We can take an element of the set big Y. This is just an even positive integer. We'll call it little y. And we can see that y has this preimage, y minus 1, under the function f. So in other words, we're saying here that f of y minus 1 equals y. And that's clear because f of x equals x plus 1. And y minus 1 is an odd positive integer, since y is an even positive integer. So that means that y minus 1 is an element of the set x. And that means our function is surjective. And since we showed that it's both injective and surjective, that means it's bijective. So we show that these two sets have the same cardinality, or in other words, the same size. And this is different from the last example because this time we dealt with infinite sets. Let's see another example with infinite sets. We'll let x be the set of natural numbers, and we'll let y be the set of integers. So the natural numbers are 0, 1, 2, 3, and so on, going up. The integers include negative, so 0, minus 1, 1, minus 2, 2, minus 3, 3, minus 4, 4, and so on. And we can actually show that these sets have the same cardinality. So we just need to demonstrate that there's some bijection between them, and we'll find the bijection. And what we're proving here is that the set of integers is countable. So we'll define a piecewise function this time. Piecewise means the definition will be different depending on what the value of x is. So we can define it with multiple cases. And for this piecewise function, we'll only use two cases. If x is even, we will let f of x equal x over 2. And if x is odd, then we'll let f of x equal minus the quantity x plus 1 over 2. To check that this f is well defined, we just need to check that for any input from the set x, we get an output which is in the set y. We see that for an input from the set x, that input's going to be a natural number. If the input is even, the output of our function is x over 2. And x over 2 is going to be an integer if x is even. And if x is odd, then the output is going to be minus the quantity x plus 1 over 2, which will be an integer if x is odd. This means that the output of our function f is always in y, because y is the set of all the integers. So our function f is well defined. And that bullet just summarizes what I said. For injectivity, checking this is very similar to the other cases, except with this problem, we need to be careful because it's piecewise. So we have different cases that can happen with the injectivity. So if we have f of x1 equals f of x2, then we either have f of x1 greater than or equal to 0 or f of x1 less than 0. If f of x1 is greater than or equal to 0, then also f of x2 has to be greater than or equal to 0 since they're equal. And that means that x1 over 2 must equal x2 over 2. Because if f of x1 is greater than or equal to 0, it means that f of x1 equals x1 over 2. And if f of x1 is greater than or equal to 0, as we said, that means f of x2 is also greater than or equal to 0, which means that f of x2 equals x2 over 2. So this is how we get the x1 over 2 equals x2 over 2. On the other hand, the other case is when f of x1 is less than 0. And in that case, we get f of x2 must be less than 0 since they're equal. And that means that f of x1 equals minus quantity x1 plus 1 over 2. F of x2 equals minus quantity x2 plus 1 over 2. Thus, minus quantity x1 plus 1 over 2 equals minus quantity x2 plus 1 over 2. So in either of these cases, we can solve the equation to get x1 equals x2. And that means f is injective. Now we just need to check surjectivity of f. So we can consider some element of the set big Y. And we can break into cases for this, just like we did with the injectivity. So for an element of the set big Y, it can either be non-negative or negative. So if it's non-negative, we'll say this element is little y, then the preimage will be 2y under the function f. And we're saying there, in other words, that f of 2y equals y. And that's if y is non-negative. And we can see that this preimage, it is an even natural number. So it's even, but most importantly, it's a natural number. It's an element of big X. Now we need to consider the other possibilities for y. Y can also be negative. So if y is a negative integer, then we see in that case, the preimage of y is going to be minus 1 minus 2y. And how to get that? Well, we can take this and we can say minus quantity x plus 1 over 2 equals y. And then we can solve this for the x. We multiply both sides by minus 2. We get x plus 1 equals minus 2y. And that means x equals minus 1 minus 2y. So that's how we got that preimage. And the thing I want to note about that preimage is that if y is negative, y is a negative integer, this means that y is less than or equal to minus 1. If y is less than or equal to minus 1, that implies that minus 1 minus 2y is greater than or equal to 1. And minus 1 minus 2y is clearly odd, but the fact that it's at least 1 means that it's an odd natural number. So we saw that in both cases for the y, we get a natural number in both of them. One of them's even, one of them's odd, but they're both natural. This means that the preimage is in our set X, the set of all natural numbers. So we just showed that f is surjective. And that means that f is bijective because it's both injective and surjective. So our sets X and Y have the same size. In other words, we showed the integers are countable. Now, sometimes it can be really messy to write an explicit bijection between two sets. So there's another tool for showing that they have the same size, and it's a lot easier. And it's called the Cantor-Schroder-Bernstein theorem. And it says that if there is an injection from x to y, and there is an injection from y to x, then there is a bijection from x to y. And this theorem is pretty obvious when x and y are finite sets, but less obvious when they're infinite. In this class, we're not going to go over the proof of the theorem. It's a theorem that you will see in an analysis class if you take that later on. But we will see why this theorem makes things so much easier. And we'll see some examples. First example, let x be the set of natural numbers, and let y be the Cartesian product of x with itself. So I write that as n squared. So this is the set of ordered pairs x, y, where both x and y are natural numbers. And we want to prove that the cardinality of x is the same as the cardinality of y, which might seem not very intuitive. So it might seem like y is much larger than x, but no, actually they have the same size as sets. And we can prove that there exists a bijection between these sets by using the Cantor-Schroder-Bernstein theorem, instead of actually explicitly writing the bijection out. And I'll just note that by proving these sets have the same cardinality, we are showing that the Cartesian product of the natural numbers with itself is countable. So we need to define some injections going both ways. Our first injection, and we haven't shown its injection yet, so I'll just call it a function for now. It's a function f from x to y, and we'll define it by f of x equals the ordered pair x comma 0. We can see that f is well defined because if x is a natural number, then the ordered pair x0 is an ordered pair of natural numbers. So that ordered pair is an element of the set y. We can also see injectivity pretty easily. If f of x1 equals f of x2, then that means that the ordered pair x1 comma 0 equals the ordered pair x2 comma 0 by definition of f. That means that both of their coordinates have to be equal to each other. The x1 and x2 have to be equal, and the zeros we already know are equal. So we get x1 equals x2, which means f is injective. Now, instead of proving it's surjective, which is not, we can just provide another injection which goes the opposite way. So we need to define a function g from y to x. And we'll define this g, and since its inputs are ordered pairs, so we'll call its input yz for some ordered pair yz, and we'll define g of yz equal to 2 to the y, 3 to the z. So we need to see that g is well defined, and we need to see that g is injective. First, we see it's well defined because if y and z are both natural numbers, in other words, if the ordered pair yz is from our set y, then that means that 2 to the y, 3 to the z is also going to be a natural number. And that means that 2 to the y, 3 to the z is an element of x. So our function is well defined going from y to x. Now we can check injectivity. If we have two inputs to our function, we'll call them y1z1 and y2z2 because our inputs are ordered pairs. And we assume that g of y1z1 equals g of y2z2. Then that means that by definition of g, we have 2 to the y1, 3 to the z1 equals 2 to the y2, 3 to the z2. And we know that these y1, z1, y2, z2 are natural numbers. We also know this fact. We'll actually talk about this fact more later, but for now, we'll just assume it's true until we talk more about divisors. There's this fact that every positive integer has a unique prime factorization. And by that fact, and the fact that y1, z1, y2, z2 are natural numbers, we can see that y1 equals y2 and z1 equals z2. And that means that the ordered pairs y1, z1, and y2, z2 are the same. They're equal. So this means that g is injective. And we show that there's an injection from x to y and an injection from y to x. So this means that there is a bijection between x and y. In other words, the cardinality of x equals the cardinality of y by the Cantor-Schroder-Bernstein theorem. Let's see a second example. And this one will maybe seem a little messier than last. Let x be the set of natural numbers again, but this time let y be the set of rational numbers. And we're going to show that these two have the same cardinality. And this is going to imply that the rational numbers are countable, which probably would have seemed surprising before the last slide, but after the last slide, probably this seems like it should be true. So we're going to define a function, f from x to y, and it will be defined by f of x equals x. So it's just the identity function. And we can see that this is well defined because any input x from the set x, and input x, which is a natural number, the output is going to be x, which is going to be a natural number, and any natural number is rational, so the output is in the rationals. So our function is well defined. We can also see that it's injective immediately, because if f of x1 equals f of x2, by definition of f, since it's the identity function, that tells us x1 equals x2 immediately. So f is injective. Now we just need to define an injection the opposite way. This is the more interesting injection. We'll define this function g from y to x. And we're going to use the fact that elements of y can be written in a simplified way. So given any element of y, since y is a set of rational numbers, we'll write it in simplified form as y equals a times the quantity b over c. A will equal either plus or minus 1. So there's only two possibilities for a. B is just a natural number, and c is positive. And b and c have no common divisors besides plus or minus 1. So we know every fraction can be written in simplest form. So this is just the simplest form for it. A is telling us the sign, and b over c, that's giving us the numerator and denominator, their absolute values. And if our number y is 0, then we can write this with a equals 1, b equals 0, and c equals 1. And this satisfies the property that b and c have no common divisors besides plus or minus 1. And if we chose for 0, if we used b equals 0 and c equals something else besides 1, for example, c equals 2 or c equals 3, then b and c would have an extra common divisor besides plus or minus 1. It would be whatever value we chose for c would be a common divisor. So this is why if our y is 0, then we're going to choose c as 1 by the way we defined it in this bullet. Okay, so we've discussed this bullet. Each element from the rational numbers can be written in simplified form. And we're going to use that simplified form to define our function g. We're going to define g of y equal to 2 to the b, 3 to the c, 5 to the a plus 1. So the product of those three prime powers. And we'll first check that g is well defined, then we'll see that it's injective. If we have y equal to a times b over c, which is an element of y, big Y, which is the rational numbers, and by the properties of a, b, and c that we wrote up here, a equals plus or minus 1, b is a natural number, and c is positive. That implies, since a is plus or minus 1, that implies that a is at least minus 1. Since b is a natural number, that implies that b is at least 0. And since c is positive, this implies that c is at least 1. That means that the number 2 to the b times 3 to the c times 5 to the a plus 1 is in the natural numbers. So even though it's possible for a to be negative, that a plus 1 guarantees us that the exponent is non-negative. So this will be a natural number, this product right here. So that gives us g is well defined. Now we need to check injectivity. So if we have g of y1 equals g of y2, that means that y1 and y2 must have the same values for a, b, and c if we write them in simplified form. And this, you can check this. So there are a few details to check here, but I'll leave that to you to think about. And if y1 and y2 have the same values for a, b, and c when we write them in simplified form, this means the a, b, and c values, we can go back to the definition of those. Those are defined by whatever y is. Whatever y is, when we write it in simplest form, a, b, and c are determined by whatever that simplest form is. So b is determined by the absolute value of the numerator, C is determined by the absolute value of the denominator, and A is determined by the sign. So that tells us that the y1 and the y2 must be equal to each other because both of these fractions have the same simplest form. And if you can write two fractions, both of them in simplest form, and you get the exact same form, it means they're the same fraction. So since the a, b, and c values that we get are the same for both y1 and y2, that means that y1 and y2 are both written the same way in simplest form, and thus y1 and y2 are the same fraction. And so y1 equals y2, that means that g is injective, because all we assumed was that g of y1 equals g of y2, and we derived that y1 equals y2. And like I said, there are a few more details to work out for this part right here, or this part right here, this second to last bullet. So that second to last bullet saying that y1 and y2 must have the same values for a, b, and c. So the reason for this, a hint for the reason I'll mention, is if we go to the last slide, this bullet right here. So the reason is very similar to the reason that we used in this bullet. The definition of our function g is slightly different here. So our function g only has inputs for y and z here, and our function on the next slide has 3 inputs for the a, b, and c. But the reasoning for why we get the same a, b, and c for both y1 and y2 on the next slide is pretty much the same idea as this third to last bullet right here, this one right here. I'll let you think about that yourself. So this right here, the idea for this is coming from the unique prime factorization and the fact that a, b, and c are all integers. Okay, so on to the next example. And this example, I guess I'll mention the end of this. So we talked about this second to last bullet, y1 equals y2, so g is injective. And so we showed that we have an injection going from x to y, and we have an injection going from y to x. So by the Cantor-Schroder-Bernstein theorem, that means that there's a bijection between x and y. So x and y have the same cardinality. So we showed that the rational numbers are countable here. And we're going to look at one last example in this video. So we're going to see an example of two sets that have different sizes. So we're going to show here that there cannot be a bijection between these sets. And our first set will be the natural numbers. Our second set will be the reals. So we're going to show that the reals are not countable. And this is going to imply that the reals and the integers have different sizes as well, because we know that the naturals have the same size as the integers. So if the naturals have a different size from the reals, then the reals must be different from the integers in size. Same with the size of the reals and the rationals. They have different sizes. So the reals are much larger than the rationals. So we're going to prove that the reals are uncountable. And we're going to do a proof by contradiction. So we'll suppose for contradiction that there is some injection f from the reals to the naturals. This has to exist if the reals and the naturals had a bijection. So if they were the same size, there would be a bijection, which means there would have to be an injection from the reals to the naturals. So that's our assumption for contradiction. And we can restrict this injection to the real numbers in the interval, the open interval from 0 to 1. So we can restrict f to this open interval from 0 to 1, and we get an injection g from the open interval 0 to 1 to the natural numbers. So we take an injection from all the reals to the natural numbers, and we just restrict it to the interval of reals from 0 to 1, the open interval. And it's still an injection if we restrict it. And we'll give it the name g for the restriction. And this allows us to make a list of the real numbers. In order to make this list, we'll first make a list of the natural numbers. We know they can be listed. We can just write them 0, 1, 2, 3, 4, 5, and so on. So it's an infinite list, but we can list them just counting them, starting from 0 going up. Then under each of the natural numbers, if that natural number has a preimage under the injection G that we defined, so if there's a preimage under G, we'll write the preimage under the natural number n. Now, it's possible that n has no preimage. We only know that G is an injection. We don't know that G is a surjection. So there could be plenty of values of n that don't have any preimage. But if there is a preimage, we'll write it under n. And we'll note that since G is injective, each n has at most one preimage. So we can just take our natural numbers 0, 1, 2, 3, 4, 5, and so on. And we can just write under the ones that have preimiges what the preimage is. So we can say, if this one has a preimage, some real number, we'll call it like RI1, some real number there. If this one has a preimage, we'll say RI2. Maybe this one is the next one with a preimage. We'll say RI3 there. And maybe this one also has a preimage, so we'll say RI4. So we see that each of the natural numbers, since G is injective, it has at most one preimage. So we'll write at most one preimage under each one. Then once we've written all the possible preimages under them, if there's any gaps, like the gap we have here, gap we have here, gap there, we can get rid of the gap. And this is going to give us a list of all the real numbers in the interval 0, 1, the open interval. Because this injection G, it's defined on all of those real numbers in the open interval from 0 to 1. We know each of those real numbers, it has a distinct output in the natural numbers from any of the other real numbers in 0, 1. And so that output must have that real number from 0, 1 as its preimage. So any real number in 0, 1 is going to show up on our list. And we can remove those gaps. So we can write this list instead of a big gap and then RI1 and then a big gap and then RI2. We can just write it RI1, RI2. We can just ignore the gaps, RI3. So we can just see what's the order we get. So we have our list. We remove the gaps. So we remove any natural numbers n that don't have a preimage, which is removing the gaps. And so we get a list of the real numbers in 0, 1. And we have a list of the real numbers in 0, 1. We can list them R1, R2, R3, and so on, just like we'd be listing the natural numbers like 0, 1, 2, 3, and so on. So assuming that we have this injection from the reals to the naturals, this gives us some list of the real numbers in 0, 1. And we list them in some order. We don't know what the order is, but we know there's some order that we can list them where they go R1, R2, R3, R4 for some different real numbers, R1, R2, R3, R4, and so on. And again, all these real numbers are from the open interval from 0 to 1. And every real number in that interval is in our list. So first thing we're going to do, we're going to write each of these real numbers in decimal form. And since these real numbers are in the open interval from 0 to 1, note that all of them only have digits to the right of the decimal. So I'm going to write an example of our list. So let's say we have I'll put it in this top left corner. We have R1, R2, R3, R4. I'll just do 5 of them for now. And I'll draw some examples of what they could be. So we have 0 point something here. Let's say 7, 6, 5, 4, 3, ... So it has more digits too. This one, let's say it's 0.121212 ... Let's say this one is 0.3333 ... Let's say this one is 0.2500 ... So it's like all zeros after that. So that R4 is actually 1/4, but we're just writing it with a bunch of zeros following it. R5 right here, let's say this one is 0.999 and so on. Okay. So we have this list, and this is supposedly a list of all the real numbers in the open interval from 0 to 1. And I should actually change that last one, because that last one, it's 1 right there, right? We have 0.999. If we have 9s repeating, that's equal to 1. And this is not an element of the open interval from 0 to 1. It's an element of the closed interval, but not the open one. So I'll change that last one to keep it in the open interval. I'll make these all 8s. Now we're fine. Okay, so there's our list. And we now need to show a contradiction somehow, because this is a proof by contradiction. So all we need to do is construct a real number that's not on the list. I'll mention a little more about this real number. It's a real number which is in the open interval from 0 to 1, which is not on the list. So this would be a contradiction, because supposedly this is a list of all the real numbers in 0, 1. So if we can construct some real number that's not on the list, that would contradict what we're saying in the second bullet. So we just need to construct this real number somehow. And we're going to construct this real number. I'll put it right here. So it's going to be Q equals, and I'll make that a little smaller. Q equals, so I have 0 there, same as the other one, 0 point something. And then for each digit, we're going to look, if we're doing the ith digit, we're going to look at the real number r sub I in our list. And we're going to look at the ith digit of r sub I. So this is called a diagonal argument here. We're going to construct this real number that's not on the list by taking the diagonal of the numbers on our list and changing the diagonal. So we have 0 point something. Then we look at R1. We look at the first digit of R1. This is the 7. We look at the second digit of R2 after the decimal. That's the 2. We look at the third digit of R3 after the decimal. This is the 3. We look at the fourth digit of R4 after the decimal. That's a 0. And then we'll look at the fifth digit of R5 after the decimal. This is the 8 right here. Okay, now for each digit, to get the ith digit of Q after the decimal, we look at the ith digit of Ri after the decimal. We'll call it Di, at least in this bullet here, just to make the notation easier to follow. And if this Di is at least 5, then we'll let the ith digit of Q be Di minus 5. If Di is less than 5, we'll let the ith digit of Q be Di plus 5. So let's see what this means for our Q here. So first, with R1, the way I've written it, the first digit of R1 is a 7. So we have D1 equals 7. That means D1 is greater than or equal to 5. So we'll let the first digit of Q be D1 minus 5. D1 7, so D1 minus 5 is 2. So we got 2 right there. Okay, the second digit of Q, we need to look at the second digit of R2. Second digit of R2 is 2. That means that D2 is 2. So D2 is less than 5, which means that we'll let the second digit of Q be D2 plus 5. So we get a 7 there. Now we look at the third digit of R3, this 3 right here. That means D3 equals 3, and that means that D3 is less than 5. So the third digit of Q after the decimal is going to be D3 plus 5, which will be 8. Then we go on to R4. R4, the fourth digit after the decimal is 0. So that means D4 equals 0. That means D4 is less than 5. So the fourth digit of Q after the decimal is going to be D4 plus 5, which is 5. And we'll do one more. So we have the fifth digit of R5 is 8. That means D5 is 8. That means D5 is greater than or equal to 5. So the fifth digit of Q after the decimal is going to be D5 minus 5, which is 3. And we can just keep on going like this if we have R6, R7, and so on. And I claim that that Q is nowhere on the list. And so this Q not on list, we constructed it so it wouldn't be on the list. And that's how we get the contradiction. So I'm going to erase that little note underneath about the 0.9999. Although that thing about the 0.9999, we're going to see something on the next slide which closely related to that. So there is an issue here we have to be careful about. We were careful about it, but I'm going to talk about on the next slide what happens if we're not careful. So Q is not on the list, contradiction. So that's how we finish the proof. We got a contradiction. It means that there could not have been an injection from the reals to the naturals. So the reals have a different size from the naturals. In other words, the reals are uncountable. So now we're going to discuss a little bit what would have happened if we were not as careful with that proof. So I claim we were pretty careful when we defined the ith digit of Q. In order to get the ith digit, we looked at the ith digit of Ri. We called that di, and then we considered two possibilities. If di was at least 5, we made the ith digit of Q di minus 5. And if di was less than 5, we made the ith digit of Q di plus 5. There's other ways that we could have thought of to define Q, other natural ways. And some of those ways would not have given us this guarantee, which gave us the contradiction, which was that the number Q is not the same as any other number on the list. And the contradiction we got was that that list was supposed to have all the real numbers in the open interval from 0 to 1. And this Q is a real number in the open interval from 0 to 1, but it's not on the list. So if we had defined this another way, it would have messed up the proof. And let's see one way that the proof can be messed up. So for example, you could try defining the ith digit of Q to be di plus 1 if di is at most 8 and 0 for di equals 9. And you will run into issues with this. So for example, if you have your list of reals, R1, R2, R3, R4, and so on, and the first number on the list is written 0.899999 repeating forever. And for the numbers on the list after that, you have the di, which is the ith digit of Ri, equal to 9 for all I greater than 1. Then by how we define the Q right here, in the second to last bullet, our Q value for the first digit of Q after the decimal, we would take the first digit of R1, which is 8, we'd add 1, so we get 9 for that. And then for the other digits, we would look at the ith digit of Ri for each I greater than 1. These are all 9, so we would get 0. So we get 0.9000 repeating forever. And notice here that the R1, which was 0.89 repeating forever, that's equal to 9/10. And 9/10 is the same as 0.90 with the zeros repeating forever. And that's Q. So we constructed a Q which was actually on the list. So that doesn't give us the contradiction. So using this construction for the Q would not actually work for the proof, even though the idea seems mostly right, but there are some cases where the proof gets messed up. So with this proof, you have to be especially careful. So that's why we defined the ith digit of Q the way that we did. And there are multiple ways to define it which work out, but like I said, you have to be careful or else you will end up with a problem like the one that we see in these two bullets. So that brings us to the end of the video. We saw a lot of examples of sets that have the same size and an example of some sets with different sizes, which that example actually gives us lots of examples of sets of different sizes. So we will continue to talk more about sets and functions later on. Thanks for watching.